Good morning, everyone. I think there are 8 participants, no, 9 now. That's good. Welcome to the Zoom-based lecture. And could someone please just confirm on Slack that you can actually hear me? Okay, thank you. That's great. So is the sound actually reasonably clear? Okay, great. Yeah, so let's get started. Thanks for joining this morning by Zoom. I am, of course, at Lake Constance at the German-Swiss border right now at my mom's place. So I hope the connection is going to hold up reasonably well. It wouldn't be a problem with the outside connection. It would be more like a problem here within the house where I'm using some kind of Ethernet over power setup. Let me respond to Mohammed here. He's asking for the URL. Let me maybe repaste that URL if I can. Oh, let's see. Whoops, nope. Here it is. Okay, so I repasted that URL. So let's get started now. The main goal for today, well, there's several goals. We're ambitious as usual. And also, I'm trying to figure out what best to do if you want to ask a question. But I think you can probably just unmute yourself and interrupt the lecture. I think there's also a way to raise one's hand symbolically. Let me see. I don't see that right now, but that should be somewhere. You can also perhaps just make yourself noticed on Slack. Let me actually close that thing here, and then we'll be able to see something. Okay, great. All right, so let's get started with an overview. So I'm going to keep my eyes on the Slack here on the right. Are you able to see the screen as well? Great. So basically, where we stand, I hope you all had a nice spring break and are well rested and had a nice time, maybe a little bit away from things. So let's recap and figure out where we stand. So basically, we've covered pretty much chapter 4. Section. Somehow this is locked. Yeah, there we go. Section 4.1 through 4.4, and for now, we're not going to cover 4.5 and 4.6 explicitly for now. We'll cycle back to them at appropriate times, but right now we're going to focus on getting started with chapter 5. So right now there are 2 open projects, which are both team projects, and the main one we're going to focus on right now is going to be project 3A in conjunction with chapter 5 in our notes on program representation and interpretation. So this week we're going to kick that off, so you can start making progress on that material and on that project that's tied to the material. And the other project that's open but has a much later due date, more like mid-April, is project 2B, which allows us to study some advanced functional programming techniques that have to do with what's called higher kinded typing, which is kind of taking generics to another level where the generic type parameter can be not only a type, but also what you call a type constructor, such as list of type T or queue of type T or tree of type T, those kinds of things. So we'll have to cycle back to that because the way I set that up now is optional extra credit for undergraduates and required for graduates. And if for whatever reason, let's say you're working with a team where your undergraduate members prefer not to do project 2B, then please form a separate team just for the purpose of 2B, okay? And we can be a little more flexible with team composition there. We can go up to 3, but the teams for project 3A and following should have size 2. All right, let's see. So let's take a look at these projects. So as I mentioned here, so 2B will be due in mid-April, and you should get started on this at some point and just familiarize yourselves with the corresponding example, which is expressions algebraic scala. And if you kind of follow that as a guiding example, then it becomes, let's say, a relatively straightforward translation from your solution of project 2A to the solution of project 2B. So basically, let me see, let me try to explain this. Okay, so if you look at the non-functional requirements, because it's basically redoing 2A, but in this kind of higher kinded algebraic style. So in other words, if you compare expressions scala to expressions algebraic scala, okay, and you kind of capture or understand the steps to go from expressions scala to expressions algebraic scala, then the requirement for, or what it takes to complete project 2B would be to apply those steps to your shapes solution and produce a shapes algebraic solution that looks like expressions algebraic, but where it deals with shapes, okay? So this just, this is intended just to kind of give you the overview of that project and get it kicked off, okay? And I would say start working on it on the back burner, and then we'll cycle back to it. That's usually better done in person, and it's going to require some communication, some interaction during office hours. So as I said, you know, as it says up here, it's required for graduate students, and it's optional extra credit for undergraduate students. So if your team, if your team includes undergrads and they want to do the optional extra credit, that's fine. You know, if they don't, then they should decide up front. And then you may want to form, if you're a graduate student, just form a separate team that will coexist with your original team, but will focus only on project 2B. So any questions right now about project 2B? Mostly these would be organizational questions. Okay, looks like no questions right now. Okay. I'm just trying to make sure that I'm actually paying attention to everyone here. But so as I said, if you have a question, try to unmute your microphone and just interrupt the lecture. Or somehow I'm not seeing this. I thought there was some way to say raise hand, or you can use annotate to um, call my attention or whatever. But for some reason, I'm not seeing that raise hand feature here, and I thought I saw that, but maybe that's, I might be remembering Adobe Connect. Okay. Oh my goodness. Okay, testing, 1, 2, 3, testing. Hello, testing. Thank you, Mohammed. I hope it stays okay, but I will pay attention to that Slack. So I will repeat anything that you might have trouble hearing. Okay. So I'm going to close this project 2B window now. All right, so let's see. Okay, that's great. Thank you, Mustafa. So the raise hand, I think, will work in the participants tab then. That's good. Okay. So let's take a look here at project 3A then, so we can get started here. It's not going to be very meaningful until we start actually making some progress on the material, but just organizationally. So this is due on March 26th, tentatively, which is, let's look at the calendar. So March 26th would be a Monday, right? So I did it so that we have that whole weekend. And so let's start talking about some of the material and then come back to the project. Do start looking at the examples. You know, we'll do that as part of the lecture as well. So, okay. What are we going to look at here? So what do we mean when we say program representation and interpretation? So this is all about the under the hood mechanisms for taking a program source and getting to a point where we can actually ultimately execute the functionality represented by that program. Okay. So this involves different artifacts, so-called source artifacts, as well as various generated artifacts. And it involves a number of different tools that will start with that source and then take that source to these subsequent stages and end up producing an artifact that is actually the executable program. All right. So this is basically something that we do frequently. You know, whenever we work on a project, we start with source code, and then we build that project. And the build process involves basically this tool chain. And then we can say run, or we can deploy to a server, or we could deploy to a device or so, right? So for example, if we develop an Android app, we have to deploy that usually to some kind of physical or emulated device, right? And server-side software is similar. You know, we deploy to a server, whether that's a physical server or a hosted server, doesn't matter that much, but then there's some mechanism for that program to run on the server, or just on your desktop or laptop computer you just run locally after the build. But what we're going to look at in more detail is what it takes to perform a build, what artifacts, source and generated artifacts and tools and corresponding stages are involved. So if you want more detail beyond my lecture notes, there's a great reference. This is a free online ebook by Torben Mogensen. So this is a really good book. It defines all the various concepts and talks in depth about the techniques and tools. All right, so to look at this tool chain, so normally there would be a nice, slightly fancier diagram, but what we are looking at here, and let me know if there's any issue with the font size, and I'm just going to zoom in a little bit. The regular font indicates some kind of artifact, an actual some kind of document or file or so, and the things in italics represent a tool or stage in the build process. So we typically start basically with a string that represents our program that is stored in a file. So that would be the source file, right? That would be right here. Then what happens with that? So ultimately what allows us to execute the functionality that source represents? Well, so the first step is typically what's called lexical analysis. In lexical analysis, we take different characters in the source file and convert those into what are called tokens. And tokens could be identifiers corresponding of one or more characters. So, for example, variable names or class names, etc. All of those things are identifiers. Those are a kind of token. And other tokens would be symbols, such as an open paren, a closing paren, or operators that are composed of multiple symbols. So, for example, less than or equal, that's a single operator, but it consists of more than one symbol, right? So the less than sign and the equal sign, but that would still be a single token, okay? So that's the idea of tokens. And then we'll have to look a little bit at mechanisms for, let's say, for actually performing this conversion of just individual characters to tokens, and we'll talk about how to represent a sequence of tokens. But a sequence of tokens is still a flat sequence, so one thing after the other. What happens after that is we have to start actually understanding the deeper structure that isn't yet in the sequence of tokens, but that we envision when we look at a program. So let's take a look at a program just to make sense of this. So, so pretty much anything. So even this build file, okay, which is kind of, it's kind of a Scala-based domain-specific language. But let me just motivate briefly what I mean by structure beyond just the sequence of tokens. So if we looked at this build file as a sequence of tokens, so the sequence of tokens already ignores all white space, such as new lines, spaces, etc. Okay, so the first token would be name. Okay, second token would be this assignment operator, : equals, and then the next token would be this string literal, okay, and so on. But then it gets more interesting on line 7. So we see, okay, there's a token which is of the variable Scala C options. Then there's an operator consisting of 3 symbols, but this is still a single token. Then there's another token which is this seq, SEQ, representing the companion object name of the Scala sequence collection. And now it gets interesting, okay? So now there is an opening parenthesis. So this is going to set the stage for something interesting. The opening parenthesis is a token by itself consisting of just this one symbol, okay? Then we have a few other things, and now there's an interesting thing because we have a closed parenthesis here, a closing parenthesis. Is everybody with me so far? The thing is, so when you just look at these things in isolation, it's not very interesting. But as we know intuitively and conceptually, the whole point of having this closing parenthesis here is to close the parenthesis that was opened earlier. So in other words, there are associations between some of the earlier tokens and some of the later tokens that the idea of a sequence cannot capture, okay? So that is the essence pretty much of, or the problem that this second stage, which takes a sequence of tokens and produces an abstract syntax tree, is in charge of. So this stage is called syntax analysis or parsing. So the role of that is to take a sequence and create a richer, usually tree or graph structure from that, okay? So when you look at line 7 in this build file, line 7 would look more, after syntax analysis, right? Sequence of tokens is what you see here, right? Basically, just keeping in mind that there are, that a variable name is a single token, a multi-symbol operator is also a single token, etc. So there are formal rules for that, which are language specific, but it's pretty apparent what those would be for just from looking at the at an example. So what does the syntax analysis do then? It does something much more sophisticated. So it takes these tokens, which are a sequence, and then it builds some kind of richer and deeper nonlinear structure from them. So here, for example, just for line 7, you could envision that structure having a root node corresponding to the double plus equals, meaning really append and becomes, right? So it's like an increment, but we're incrementing the mutable sequence Scala C options by the sequence that we see here, the sequence we're actually constructing here. So this would show up as, if you think about the operator becoming the root of the abstract syntax tree, and whatever is to the left of a binary operator becoming the left child, and whatever is to the right becoming the right child, then you would have for line 7 a root node with append and becomes, which is a way of saying, or which is what double plus equals represents, right? That would be the root. The left child would be the variable Scala C options, and then the right child would be this sequence. Now the sequence itself is a subtree, so it would have some kind of node representing the fact that it's a sequence, and then the children in the order that actually matters in the case of the sequence would be those three strings: deprecation, feature, and unchecked. Now, where do the opening and closing parentheses go? Do we still need them? So the thing is, right, these parentheses, we only need them when we're looking at this flat sequence of tokens to introduce some additional non-flat structure. So we have to say, okay, the sequence starts here, the SEQ indicates that, but we have to know where that sequence closes. Otherwise, we think that everything in the remainder of the file will be part of the sequence, but it shouldn't be, right? There's other stuff going on there. But then once we build a tree and we say, well, there's a sequence node, and that node has those three strings as children, then the parentheses are no longer necessary. So internally, they're not necessary. But if we then say, well, let's print that node back out, then we can always bring them back, because we can have some kind of two-string method. So that happens to be called an unparser, something that, or a pretty printer, something that takes an abstract syntax tree and converts it back into the original program source. You can bring it back then, but you don't need to store the parentheses internally. Although in some cases, it would be helpful to have the parentheses, for example, to give better error messages. In those cases, it would help. Anyway, so I'm just kind of trying to motivate some of these ideas. So now we'll come back here. So this gives us a little bit of an understanding what happens when we go from the sequence of tokens by performing syntax analysis to generate an abstract syntax tree. And the abstract syntax tree is the principal internal data structure that we have in a compiler toolchain. So that's an internal representation of the program as a tree. Now, there could be now multiple, let's say, attempts to improve that tree and to transform it. So those kinds of things could be static checks, for example, making sure that everything checks out, that, for example, you're not trying to add a sequence and a number, right, numerically. So you can take a sequence and add that number as another item if the type of the items of the list is compatible with the type of that number, right? So those are the typical kinds of static checks you have. They're usually type checks or other kinds of checks, like let's say analyzing whether part of your code is unreachable, like you have a return statement somewhere and there is more code after the return statement, then a static check could very easily detect whether you have unreachable code that is simply superfluous because it could never be reached in any path or execution path through your program. Then other important transformations are optimizations, such as, let's say, discovering that there are certain sub-expressions, let's say 3 plus 4, that occur in multiple places, and then you can transform the program automatically in such a way that it computes that only one and then just refers to the result wherever it needs that value. Okay, so those are typical things that happen kind of in the middle to the transformed abstract syntax tree. And then we perform the basically last step of the build, which is code generation, meaning we take that syntax tree internal syntax tree, and then we produce another artifact which represents the executable machine code or bytecode, right? So when we use, let's say, C++ or C, there are a number of languages like that. The compiler ultimately, or the tool chain, because it's usually there's a linking step, which I haven't mentioned here, but typically the result of the build process is executable machine code, where you can just say, you just run it directly. So we can try that here. So I got that little terminal here, so we can say we can write a little bit of C code here. So now I'm just writing kind of from scratch a piece of C code. So int main, wow, that's always hard now. So arg, int arg C, character array argv. Well, I might have to edit it after this, but so these are the command line arguments, and then I can say something like put string hello world. Okay, close. All right, so now I got this file, and I can try to compile it, and not bad, right? So I got the command line arguments right, but this is just a warning, and now there should be a piece of binary code called by default a.out, and if I run that, it'll say hello world. So here's your hello world in C, okay, and if we say file a.out, it says exactly what it is. So this is machine code that can run directly here on this Linux laptop. Okay. Another aspect is that this is not exactly a standalone, self-sufficient piece of code, because there are still what's called dynamic dependencies, what's called DLLs on Windows. There's the same thing on Linux called shared objects, or in Unix in general, shared object libraries. And here is the shared object libc, which provides the library function putS for put string. Okay, so what you saw here is basically a fast track execution of the C compilation toolchain, like building manually but doing it quickly. What I could do to introduce this linking step, I could say gcc compile only, and that will give me a hello.o, which is just an object file, and we still need to link that in such a way that it becomes an executable. This is important because normally we have many source files, and each source file gets compiled separately to a .o object file, and then all of those get linked to a single executable. Okay, that's similar to let's say Java or Scala, resulting in multiple .class files. Even if you have, let's say, fewer source files, you might have more .class files. Okay, so let's take a quick look here at one of the examples. Okay. So this has a bunch of stuff in here. That's the example. Of course, that is also relevant to our study of program representation and interpretation, and it's going to be one of the guiding examples for Project 3A. So when we build this Scala project, we say something like, we could do a clean rebuild, right? So we could say sbt clean, And now we can say, of course, SBT compile, and that's basically the build process. But in fact, what really, so let me, yeah, so this doesn't have the SBT stage part. You could argue that the closest to going through the entire build process is this SBT stage task that we had in the iterators example. But compile gets us pretty close. I mean, it produces a collection of bytecode files that are pretty much ready to execute in the JVM. And you can see here how it compiles the Scala sources, that's kind of the thing it says at the bottom, to a classes folder. And if we look at that folder, so we could say tree, target, Scala 212 classes. Here's what you're seeing, right? So these are the various bytecode files resulting from the original Scala sources. And when we say SBT run, it'll basically look for one or more main methods, public main methods in any of these classes. And it knows where to find those because they're in a standard location, which is what this target Scala 212 slash classes is. So that's just the SBT, standard SBT location for the generated classes. So here it detects multiple main classes. We can, for our purposes here, we're not looking at so-called PEG grammars, parser expression grammars. We're looking at just combinator parsing, which are kind of simpler to understand. So let's choose that first main program. Now we can enter an expression. So we can say 3 plus 4, okay, minus 5. And what this will do is, and that's also the example we're going to study to understand parsing. This will basically, we could also have numbers that have more than one digit. So for example, 55. So what this will do is it will look at the input that we're about to enter, and it will perform lexical analysis, and it will find that there are some numbers, and it will find that there are some operators like the plus and the minus, and it will produce an internal abstract syntax tree, and then it will directly interpret the abstract syntax tree representing this expression, and it will give us the answer. So it'll basically do the job of a calculator. This will say 3 plus 4 minus 55 should be negative 48, right? So let's try that. Okay, so there's some error, and maybe because, oops, we have to use parentheses because this is not a very good parser, or rather the parser is not based on a very good grammar. So let's try this. There we go. Okay, so this allows only strictly binary expressions. So I cannot even say 3 plus 4 plus 5. I have to say that expression in such a way that every operator has exactly 2 children, or two operands, 2 sub-expressions. Okay, so what do we see here? Well, it succeeded in parsing this expression, and it said, well, the root of that tree is the minus, and then there's a subtree corresponding to the left sub-expression, which is the plus 3 and 4, and then the right subtree is just another number, which is 55. And this output is a representation with the indentation of the internal abstract syntax tree. And then it prints a few other things that we've studied, like size and height. Okay. And then it performs evaluation. So we could do other things like 3 plus 4 times 5. All of this basically works, in this kind of simpler way. So this is a very simple example. You might have seen similar examples in your data structures course, like 271 or similar, but we're going to start our study of the various stages of the compilation tool chain here. So any questions so far? Okay. Briefly, I wanted to mention this idea of cross-compilation. Cross-compilation means, let's say you have a deployment target, like some kind of embedded device, let's say a router or a sensor host or some kind of very simple low resource device with very little memory, maybe very slow. So what you would usually avoid is developing directly on that device. So why? Well, because it would be too slow and painful, and maybe the tools won't fit on the non-volatile memory, etc. So there are all kinds of constraints and restrictions. So a target environment that doesn't provide sufficient computational resources to develop, especially compile software in the target environment itself. So mobile phones, you don't usually write an Android app on an Android phone or an iOS app on an iPhone or let's say some kind of hybrid web app kind of thing on either of those. What you normally do is you develop on a laptop or desktop, and you try it in an emulator, and then you just deploy the result when you're happy with it to the target device, right? So that's the idea of cross compilation, which simply says that the code generation doesn't necessarily target the same platform as the one where we're developing. That's really all it says. And here's a little example that is on some kind of little travel router, a little square-shaped thing that's maybe 5 times 5 centimeters square. Very small little thing. So I'm gonna do maybe a show and tell next week. Gonna try that first and then make sure it works. And there's of course a deployment step where you can use scopy, like secure copy or file transfer protocol or whatever, to physically deploy the executable code for the target so that the target actually has it stored on itself. All right, so that's this idea of cross-compilation. So now we're going to start digging more deeply into the front-end concepts and techniques. So front-end, again, what does it take? Basically everything until we have the abstract syntax tree. So this means first lexical analysis and then syntax analysis. So lexical analysis means we're recognizing and representing tokens. Where do we start? Well, we just have characters, right? Letters, number, digits, symbols, and so on. So you have a variable, something that will become a variable, but until you perform lexical analysis, it's just a string of characters. So how do you specify which sequences of these characters are actual valid tokens, valid pieces of your language, and how do you write a tool that is able to actually recognize and then represent these tokens? And the mechanisms that we typically use for this purpose, because they're very well established and they're very efficient and very widely supported, are things like regular expressions, which are equivalent to what are called non-deterministic finite automata and deterministic finite automata. Whoops, I must have pressed the wrong key here. Okay. So these automata, you've probably seen them. The purpose is basically to recognize certain sequences of characters. So you see like circles and you're representing states, and then whenever you read a character, you perform some kind of transition, and if ultimately you reach a final state, then that sequence was a valid token of the kind you're looking for. If you reach some kind of error state, then that sequence is not a valid token. All right, so that's how these kinds of things usually work. Finite automata, whether they're deterministic or non-deterministic. So it turns out that these are equivalent to regular expressions, and because regular expressions are a character-based notation, it's easier to deal with them, whereas finite automata are diagram-based kind of technique. So that's typically a little harder in terms of the tooling for drawing the diagrams, etc. That's why we're focusing here on regular expressions, and we can look at some examples. So this is from an algorithms text, and here's a great example from genetics, and or genomics to be precise. And here we say, well, a human's genome we define as a string, and that string needs to follow a particular format to be considered correct. And that would be a triplet of CGG or AGG repeated. And at the beginning, we should see a GCG, so it's a little different. And then at the end, we want to see a CTG. So how do we express this kind of verbal description formally? And that's exactly the kind of thing regular expressions can help us. So we can say, we can use a regular expression for formally describing this pattern of character sequences. So we say from left to right, beginning to end. So we'll say, okay, it has to start with GCG. Then we need to see 0 or more occurrences. That's what the so-called clean start, KLEENE, indicates, 0 or more of something. And that's actually pretty common, and it's common because of the meaning it has in regular expressions. And now the parentheses are what you could call meta characters. They're not actually part of the pattern we're matching, They're just part of the mechanism for describing the rule. So after seeing GCG, we expect to see 0 or more occurrences of either CGG or AGG, and then at the end we expect to see CTG. And we can use this pattern to match variable length examples of strings that actually match this pattern. So here's one. So for example, if you went in here, and you tried, okay, well, I am seeing a GCG here, but then I'm seeing another GCG here, so it doesn't match this or that, right? So whatever we see around here isn't a match, but then there's a match here where it says GCG. Okay, that looks promising again. And then what do we have? Well, CGG. So that so far it matches this one here. What comes next? Well, we want to see either a CTG as the last thing or another occurrence of CGG or AGG. And we see an AGG, so we're good. Then what do we see? Again, we want to see either a CTG to indicate the end or another occurrence of CGG or AGG. And here's another CGG. All right, that's cool. And then finally, same thing. So here we're seeing an occurrence of CTG, which marks the end of the sequence. So whatever's in red here in this example, that matches the pattern. So that's something that regular expressions are extremely useful for. Something else is related more to recognizing tokens and things like that. So for example, recognizing keywords like public or class, etc. in a source. So this is like something much simpler than syntax analysis, but it's related to lexical analysis. So it's like partial lexical analysis because we're just highlighting, let's say, syntactic keywords. Then there are a few other examples like search terms. So Google actually allows searching using a regular expression, so that's maybe potentially more precise than their normal search language. But even their normal search language has meta operators like and or and parentheses and things like that. So you can try that out. Then there are a bunch of other useful applications. So even parsing or scanning a file for virus signatures. So you'd have to have some kind of database of possible virus signatures, like what pieces of code do you expect close to each other in a virus, and if you can express those as regular expressions, you can do a relatively efficient scan for these things. Other examples are processing a natural language. That's a little more ambitious. Specify a programming language. That's very common. Access information in digital libraries, etc. A lot of applications in genomics, generally computational biology, as well as computational linguistics. So that is more on the side of testing whether a string matches a particular pattern. Then the other set of examples is, the syntax highlighting, like where we're actually looking at a whole file and maybe transforming or analyzing that file in some way. And of course, some of these kinds of applications, like creating this automated documentation from a Java doc or Scala doc comment block. All right, so any questions, comments? Okay. So regular expressions are actually built on top of some kind of alphabet. So here, the alphabet happens to be just A's and B's. And let's see. These are some examples of what concatenation and these various other regular expression operators do, right? So this is order of preference in the prerequisite in the operator precedence, and parentheses bind the loosest, and then let's see. I mean, the parentheses bind the closest. So everything that's in a pair of parentheses gets priority over anything that's outside of the parentheses. So this has operator precedence 1, which is the strongest precedence, and then in the order given by this precedence number. Okay. So parentheses just mean that whatever operations you have there will have higher priority or precedence. Closure applies directly to the single character that follows the closure. So if you want to apply so closure again being 0 to as many as you want, 0 to infinity. So what applies is when you apply the clean star closure operator, it applies only to the immediately preceding character. But of course, you can group those characters together using parentheses like we did in this example, right? So we have the parentheses, meaning that you got to have all of CGG in that sequence or AGG 0 or more times. Okay. Now, let's see. Right, so that's for the parentheses in conjunction with concatenation. And concatenation just means you gotta see the characters in the order. So if I say AAB, it has to match those characters in that order, and it doesn't match anything else. Whereas closure is the one where you introduce alternatives in terms of 0 or more occurrences of a particular character or sequence of characters, and or is an alternative between one thing or another. So this is a very simple set of building blocks, but these are very expressive for specifying the tokens, the valid tokens in a language. Also, there's some kind of convenience operators like the dot, meaning wildcard, and these you can express using the others. So, for example, the dot operator, you could express by saying either A or B or C and so on, but it would be very tedious. That's why these kind of derived operators are useful, because they're easy to understand, but they save you a lot of tedious writing and reading of more complex regular expressions. Okay, so you can distinguish between uppercase and lowercase, etc. So if you want to have variables that are, or identifiers that are capitalized, you say, okay, well, initially I want anything from capital A to capital Z, or let's see, if I want to allow if I want to allow the word to start with uppercase or lowercase, I can say capital A through capital Z, or lowercase a through lowercase z in these square parentheses or square brackets, right? So again, the square brackets are kind of a meta character which wouldn't be part of the actual expression or the actual string you're matching, okay? So what we're saying here is the first character has to be either uppercase or lowercase, and then all subsequent have to be lowercase, right? And that's why this expression matches either lowercase word or capitalized, but it doesn't match anything with camel case or anything that starts with anything other than letter. And again, how do we convince ourselves that this camel case example is illegal? Well, first character here, it says uppercase A through uppercase Z or lowercase a through lowercase z. So the first letter could be either uppercase or lowercase. But then we see here all the arbitrarily many subsequent characters all have to be A through Z, lowercase. Does that make sense? So that's why, for example, camel case is illegal because simply an uppercase character further down in the word won't match. And then the for illegal won't match either because it starts with a digit, but clearly here the first factor here in this regular expression says it's got to be a letter. Uppercase or lowercase doesn't matter, but it's got to be a letter. All right, getting spam calls even over here. All right. Cool. So there's some more examples here. It's really nice, fun, and useful stuff. So you can do quite a lot of cool stuff in terms of searching or matching patterns, etc. So that's regular expressions in a nutshell. Any questions or comments so far? So please, take a look at this nice document on your own. I think really good, has good examples. In Java and Scala, you've already seen some examples of regular expressions. So of course we have to kind of represent them in some kind of Scala or Java friendly way. So what you're seeing in this set of slides is basically applying what we just saw to Java. And then what we saw in Scala is actually, let's see. All right, so 5-minute warning here. We look at I was going to look at the Sakai example. And we'll look at project 1A. I'll show you a regular expression Scala that we've already worked with, and it's actually right here. So there's this example where it says split. So this says take each line, split that line, represented by this underscore, meaning current line, current item in the iterator or collection lines, and then let's split it in such a way that it includes one or more characters that can occur in a word. That's a regular expression using this word character class. Okay, so it's a very simple one, but it uses the word character class. Let's see if that shows up here. Character class is here. Define a class of multiple characters. Okay, yeah, so actually let's refine what I was just saying. So the uppercase slash or backslash W means a non-word character, which means in this regular expression, it means whenever we find one or more non-word characters, we split the input line there. And what's left would be, so splitting by not including that. So what's left is the line converted to 0 or more words. So we get basically for each line, we get 0 or more words. And the flat map makes sure that we get a flat list or iterator in this case of those words, as opposed to a nested collection where we have for each line in the original collection, we'd have a sequence of words. Let me just show that here for a second. So Scala and say, or SBT console quick. So what we're seeing here is basically, if I say, hello world, what up, like this. So if I say split this string into or by along non-word characters like this, we should get hello world, what up as a sequence of those 4 strings. There we go. Why is it an array? Well, it's just because originally the string is basically a character array. All right. So now, if we have multiple lines, let's say we have something like iterator, this line right here, then another line, good morning, like this, stuff like this, right? And then another one, kind of like this, okay. So we have an iterator representing 3 lines. So if we now say map, and then split each line where we could say, like this, say L maps to L dot split word, uppercase word plus, so meaning non-word characters, 1 or more, right? So we can write it like this, or as you know, the underscore is just an abbreviation for that one formal argument. So what do we expect to see here? Well, for each line, we will see basically an array of the words in that line, like this. And if we say res1 to list, we see a list of these arrays, right? Whereas if we did a flat map, then we would have a single flat sequence instead of a list of arrays. You see? So now there's only one level of collection here. So that's one thing flat map's really good at. Anyway, so we're out of time for today. Let me cycle back to the notes here. Okay. So we've covered regular expressions, lexical analysis. The next thing we're going to cover is syntax analysis, especially the kinds of notations we have for defining, given we have a sequence of tokens, what is a valid order or choice of those tokens? What are valid sequences of tokens to represent a program? And usually we use grammars or similar kinds of notations for like the so-called extended Backus-Naur form, which is a way of expressing a grammar. And you can look at Mogensen chapter 3 for more details. So I recommend getting started reading these chapters 2 and 3. And we're really kind of looking at the subsequent stages of compilations in a more, let's say, streamlined way. We're not going to look at code generation. We're just looking at directly interpreting an abstract syntax tree, right? Just to be able to execute something, but we're not going to look at things like optimization much or code generation. We're going to look a little bit at maybe static checking. Okay, so these are your typical mechanisms for syntax analysis, where we write our grammar rules in basically a domain-specific language for grammars, for particular kinds of grammars. And then a parser generator generates the actual parser for our language from that source in that domain-specific language. And the YACC, Y-A-C-C, and Bison or Bison tools are examples of that. We'll take a look. And then there's some other, let's say, commonly used parser tools or libraries, and parser combinators are one option here. And that's the option we're going to look at because it's a little more straightforward than most others. So that's what we're going to do on Thursday. So any questions right now? If not, please do review your grades you've received so far and discuss any questions you might have with John. So John's going to have office hours tomorrow by appointment, I believe, tomorrow, Wednesday. So do work something out. As I mentioned, I'm going to be out the rest of this week and then back on campus for next Tuesday's class. So thanks very much for joining. We'll see each other again on Zoom on Thursday. All right, so have a great rest of the day and rest of the week.